This is the second half of 4.3. It's discovering, we're going to go through the mean value theorem. So this is very exciting. We're going to start with discovering it. So what we're going to do, I'm going to have you do this part on its own. So I want you to do this 11 through 16. But it says draw a secant line between the points A and F of A. So that's this point right here with a different color. A, F of A, and B, F of B. Remember, a secant line is just a line that crosses those 2 points. On that one, it would be something like that. Then it says draw all tangent lines parallel to that secant line. So I'm going to come up here. Somewhere in there, it looks like that. I would have a tangent line that's parallel to that secant line. And I want you to do that for this 11 through 16, and we're trying to discover something here. So go ahead and pause the video. Work down through those. While you're doing it, I'll do it also, and then we'll come back and compare them with each other. So I have all mine drawn. On that number 12, I think I could actually draw 2 lines that are tangent to that line. So here's my line, my secant line. Looks like it has 2 places where you'd have parallel tangent lines. On 13, I could not draw a parallel tangent line. There's nowhere I could draw that. I guess you could draw an infinite amount of points that cross through there, but there really is no slope there. So I don't know that you could say it was parallel. Are we good with that? It's not differentiable because there's a sharp turn and there's no slope. 14, again, I could draw a tangent line, but I don't know if there's anywhere I could draw so I could draw a secant line, but I don't know if there's anywhere I could draw a tangent line that's parallel to those. And I want you to notice it's not differentiable at that vertical asymptote. 15, you can't even draw the secant line because there's no point at A, F of A. 16, I can draw the secant line between those 2 points. It's horizontal. But normally the tangent line would be right there, but I can't draw a tangent line because that point does not exist. So long story short, I want you to notice the first 2 examples, number 11 and 12. If the function was continuous and it was differentiable, there were no sharp turns, then I could always draw a tangent line that's parallel to the secant line, like number 11. 12, I could actually draw 2 of them. On 13, because of the sharp turn, I could not. 14, it wasn't continuous. There was no tangent line that was parallel. 15, I couldn't even draw a secant line. 16, I could draw my secant line, but because that point was missing right there, I couldn't draw a tangent line that was parallel to it. Okay, now this next part, we're going to do a similar thing. It says draw the secant line between the points 2, F of 2, 5, F of 5. Draw all the tangent lines parallel to it and estimate the value of C if C, F of C is a point of tangent C. So let's do this first one together. So what it's talking about is if I draw the secant line right there, then I'm going to draw the tangent line that's parallel to it. Just going to estimate in there. It wants us to estimate where that point, see that point where your tangent line is hitting the graph, estimate what that coordinate is. Now it just wants the C value. The C value is the X value. Okay. So estimate C. So we want to estimate where that would be. So on that one, I would say it's approximately 3, somewhere in that ballpark. Okay, take just a second and work down through those. I'll do the same thing, and then we'll come back together and talk about them. All right, hopefully you paused that and you went through all those. Let's talk about it. So we did this first one, right? There's my secant line. There's my tangent line. So we approximated about 3 is the X value. On this one, here's my secant line. So my first tangent line, I just estimated. Again, this is an estimate. I estimated about 3 again. The second tangent line right there that's parallel to that secant line, I estimated to be about 4.5. This last one, there were 3 of them. Like there's my secant line. Okay. There's my tangent line. It looks like that one would be at about 2.5. And then up here again, looks like it could be tangent about the same line. I guess made about 4.5. And that point about 3.5. Now I want you to notice all 3 of these examples, it was from that point to that point, it was continuous and it was differentiable. On this one, now there's a sharp turn here, but if I just go between that point and that point all the way through, it is continuous and differentiable, not including that point. It's not at this one location, it's not differentiable, but from that point to that point in between, it was differentiable the entire time. plus it was also continuous. This one was, again, differentiable and continuous on that entire interval. So that brings us to the mean value theorem. The mean value theorem is actually pretty simple. It sounds complicated when we explain it algebraically, using a bunch of big words and stuff. But the idea is this, is if I pick 2 points on a graph, so for example, that point and that point, if the function is continuous from that point to that point, so it's continuous all the way through, including the endpoints, it has to include the endpoints, and it's differentiable between the endpoints, then if I draw the secant line, there's going to be at least one place between there. Sorry, I'm going to draw the tangent. Yeah, the secant line. Excuse me. If I draw the secant line, there's going to be at least one point between the start point and the end point where the slope of the graph, the actual slope itself, is equal to the slope of the secant line. Those will always be equal. Now, using our terminology we've talked about before, the slope of the secant line, that is the average rate of change. That's AROC. If I'm finding the slope at any given point, for example here, where it's parallel here or here, that's the instantaneous rate of change, that's IROC. So another way to say this is, with the mean value theorem, as long as a function is continuous between the 2 points and differential between the 2 points, there'll be at least one place. This one had 3 places, there, there, and there. This one had 2 places, right there and right there. This one only had 1 place. There'll be at least one place where the instantaneous rate of change IROC will be equal to the average rate of change AROC. So we find the average between the secant line, the slope of that. There'll be at least one place, this one has 3, where the instant rate of change will equal that average. So let's say that in big fancy words. So it says if f is continuous from A to B, so it has to be continuous. So let's underline that. So it has to be continuous. That's stipulation number 1. And it has to be differentiable. That's number 2. Then there's a number C in AB such that f prime of C, I want you to circle that and put IROC next to it. When the instant rate of change has to equal this, that is the AROC. That's the average rate of change. There's got to be at least one point on there where the instant rate of change equals the average rate of change. That's what they're showing right here, right? From there to there is the average rate of change. That gives us the average rate of change, whereas that point is the instant rate of change. At that one location, they're equal. And there will always be at least one place where the average rate of change equals the instant rate of change, as long as a function is, 2 things, continuous, differentiable. So informally, down below it says the mean value theorem states that given the right conditions of continuity and differentiability, there'll be at least one tangent line parallel to a secant line. Or another way to say it is the instantaneous rate of change, IROC, will equal the average rate of change, AROC, at least one time. Could be more. So let's do an example where it wants us to find this. It says given f of x equals 3 minus 6 over x, find all c which satisfy the mean value theorem on the interval from 3 to 6. Okay, so first thing I have to check is, let's make sure that the mean value theorem actually applies. So the question is that function differentiable over that interval from 3 to 6? So if you look at f of x, just figure out when it's not, sorry, I said differentiable. Let's start with continuous. So is it continuous over the interval from 3 to 6? Well, if you look at that, the only time it's not continuous is when x equals 0. So it's not continuous at 0. So from the interval from 3 to 6, it is continuous. So we're good there. The second thing is it differentiable on the interval from 3 to 6. So to find that out, I'm going to take the derivative. So f prime of x is equal to, I'm going to think of that as being, come up here, I'm going to think of f of x as being 3 minus 6x to the negative 1, just to make it easier to find the derivative. So the 3 goes away, drop the negative 1 down. So negative 6 times negative 1 is 6, x to the negative 2. So that would be 6 over x squared. So again, the question is does that derivative exist on the interval from 3 to 6? Well, the only time the derivative doesn't exist is when x is 0. So we're good. From 3 to 6, it always exists. So it's differentiable and it's continuous. So it meets those 2 requirements. That means the mean value theorem does apply. Okay, so the mean value theorem says that the average rate of change, if I find the average rate of change, there'll be at least one place between 3 and 6 where the graph will have the instant rate of change will equal the average rate of change. And I'm trying to find that value. So let's find the average rate of change first. So to do that, I need my 2 points. It's 3 something. Let me move over since my board doesn't function over there. So it's 3 something, and it's 6 something. So if I plug 3 in, I get 3 minus 6 over 3 is 2, 3 minus 2 is 1. So plug 6 in, 3 minus 6 over 6, 6 over 6 is 1, 3 minus 1 is 2. So there's my 2 points. Let's find the average rate of change. So just do the y minus y over x minus x. So a rock is equal to 2 minus 1 over 6 minus 3. 2 minus 1 is 1. 6 minus 3 is 3. So my average rate of change is a third. Okay, what I'm trying to find is when would our function when would the instant rate of change equal the average rate of change? Well, the instant rate of change is given by the derivative. So I want to find out when is the derivative, when is it equal to the average rate of change. So I just need to solve that. You can actually just cross multiply on this one if you want to. So that would be x squared equals 18. Take the square root of both sides. So x equals plus or minus the square root of 18. Now I want the c value or the x value to be between 3 and 6. A negative square root of 18 would not be between 3 and 6. A positive square root of 18, I don't know what it is, but I know the square root of 16 is 4. Square root of 25 is 5. So I know it's between 4 and 5. That means it's on the interval. So the answer is, for what c value will the average rate of change equal the instant rate of change? That would be at the square root of 18. So we just have to mean value theorem. Mean value theorem is talking about the slope. And it's talking about if the function is differentiable and continuous, then there will be at least one place where, if you find the average rate of change, there'll be at least one place where the instant rate of change will be equal to that. Picture that secant line. If you draw the secant line to get the average rate of change, there'll be at least one place where the tangent line, the instant rate of change, has the same slope, where it's parallel to it. The hard part about this one is a lot of us confuse it with the intermediate value theorem. And it comes back to this whole c. Remember, we found the c value on that intermediate value theorem. There are two different problems. It just takes practice to make sure we can tell the difference between the two. This would be something I'd add to your flashcards, mean value theorem. And the big idea behind it is I would make sure for it to apply, it has to be continuous and differentiable. And the second thing, it's when the average rate of change equals the instant rate of change, or when the secant line is parallel to the tangent line. Okay, thanks guys.